our keynote talk. Thank you.
Yeah, it's my pleasure to introduce our first keynote speaker, Laura Leal-Tergé. Laura is a professor at the Technical University in Munich, where she has established the Dynamic Vision and Learning Group. She did her master's at the Technical University of Catalonia in Spain, and then got her PhD from the Leibniz University of Hanover in Germany. She's worked as a postdoc at ETH for 2 years and then joined the Technical University of Munich, first as a senior postdoctoral researcher and then as a professor. She has received the prestigious Sofia Kovalevskaya Award and has been very active in the computer vision community. So you definitely know her from the Mod Challenge workshops and associated challenges. She has been area chair for multiple vision conferences. She's regularly organizing tutorials and workshops. She was a program chair for VACV 2021 and will be a general chair for ICCV 2024. Her research interests are quite wide. She's doing localization, where I'm lucky enough to work with her. She's doing object tracking, panoptic segmentation, instance level segmentation, and metric learning. Today, she's going to talk about recent work on learning intra-batch connections for deep metric learning. Laura, the floor is yours.
Thank you, Thorsten, for the really nice presentation. So I'm happy to be here today to talk about our recent ICML work, learning intra-batch connections for deep metric learning. And this is joint work with my student, Jenny, and my postdoc, Ismail. So let me start by introducing briefly what is deep metric learning. I'm sure you're all very familiar with it, but let's start slow. So in deep metric learning, yes.
I'm sorry if I interrupt. I think you are sharing the wrong screen. I'm
sorry.
Seeing the presenter view, but I think you might want to switch to the slides window.
Is this better?
Yes. Yep. This looks better.
Sorry. Wrong desktop. Thanks, Tobias. Okay, so what is deep metric learning? In deep metric learning, we want to learn a distance function among objects, such that if two images that I present to my network are not really similar, they get a low similarity score or a large distance. Whether if I present two images which are depicting, in this case, the same person, I get a high similarity score or a small distance. Now, this is what happens at train time, right? This is how I want to train my network. At test time, though, a simple threshold or a nearest neighbor search will do, meaning that if these two images, the distance between these two images is larger than a given threshold, then I decide it's not the same person. If it's smaller than a given threshold, I decide it's the same person. So really easy at test time, which is what makes deep metric learning so appealing for so many applications like landmark recognition, object retrieval, etc., etc. So as I said, deep metric learning is about learning a distance function over objects. So here we can see one representation, a TSNE representation, where we can see nice clusters of different objects in one of the data sets, which is a birds data set. So one can see that once we have trained our network to actually put similar objects close together and these similar objects far apart, then we can see these nice clusters, like, for example, these birds with a red hair, with a red, I don't know, sort of head, or all of these birds which are similar and all brown. I'm not really a bird expert, but apparently these are similar bird species. And these are actually nicely clustered together when our metric learning network is trained. So usually training happens with contrastive and triplet loss. So I'm here oversimplifying, right? These are the major losses for training deep metric learning networks, but of course there are nowadays new losses out there. But the classic losses are the contrastive loss and the triplet loss. So in the contrastive loss, what we're doing here is we're using one-to-one relationships. This means that we get what we call an anchor image, and a positive sample, which is an image of the same category, the same instance. For example, in this case, it's the same bike. And we get the same anchor image paired with what we call a negative sample, or a sample that does not really depict the same instance in this case. And so what we're going to do is we're going to compare these pairs, anchor and positive and anchor and negative. We can do something a little bit smarter, which is the triplet loss, which uses two relations. So what it says is the anchor has to be closer to the positive sample than to the negative sample. I'm not going to spend energy during training in bringing anchor and positive together, as long as the negative is further apart than the positive with respect to the anchor. So it's more of a comparison loss, rather than saying anchor and positive as close together and as possible, and anchor and negative as far apart as possible. Now, this all works great if we're training our network with these images and we really want to distinguish the green bike from the black bike. But what happens is that in our data set, we're going to have n sample, which means we're going to have a lot of pairs and a lot of triplets, but the vast majority of them is really uninformative. So for example, it is really obvious that this chair and this bike are not really belonging to the same class and therefore are not going to be the same instance, which means that training with these pairs or with this triplet is actually not going to be informative. It's not going to bring our network closer to better results. So in order to use contrastive and triplet loss, many sampling techniques have been presented. Most notably negative, so mining for really strong negative pairs. But still, what happens when we use, for example, a batch HB, with the contrastive and with the triplet loss, we're only taking B-halves or 2 B-thirds in the case of the triplet loss relations into account. So even if we select these samples really carefully, the relationships that we're going to take into account are only going to be very limited. The idea here is that what if we could actually use all the relations that we have in our batch? So all the relations between the samples in my batch. Can we actually construct a neural network that takes this global structure into account so that we don't have to go ahead and fiddle with the selection of the pairs or the selection of the triplets? So what we propose to do in our ICML paper is to learn these intra-batch connections. So we start with the classic feature initialization. We use a CNN to extract features from our images. And now here, the interesting thing that we do is that we're going to perform this sort of communication between samples. So how we do it is we create a graph where each sample is going to be a node. So each sample is going to be one image of the batch, either the bicycle or the chair. We're going to take its embedding that is coming from the CNN, and we're going to place it in a graph as a node embedding. And then we're going to do k-message passing steps. So message passing steps within this structure are steps which are actually learned and which actually allow communication between samples. So all that this does is it updates the feature embeddings for each of the samples. And now with these updated feature embeddings, what I can do is I can use a simple cross-entropy loss to optimize the CNN backbone and the message passing network. And we do this in an end-to-end fashion. So we go from the cross-entropy loss all the way to the CNN backbone. Now the question is, what is this message passing network doing here in the middle? So essentially what it's doing is just taking the initial feature embeddings, the ones coming from the CNN, and it's refining these embeddings according to the information of the neighboring images or the neighboring embeddings. So it's looking, let's say I'm the green bike and I'm looking at all my neighbors. I'm looking at their embeddings. And I'm trying to find out who is similar to me, who is dissimilar. Let's communicate before I make a decision on whether I am a bike or I am a chair. And this communication is actually what allows to take into account all the relationship between the samples in this batch. So let me briefly present how we actually implement message passing networks, what they actually do. So as I said, the starting point is to construct the graph. We will have as node features, the features coming from the CNN for each of the image. So remember that each node in this graph is going to be one image of my batch. And then we're going to go to the interesting part. So the interesting part is here in the middle. And this is where this information propagation happens. So we have several steps of information propagation in which nodes communicate with edges and edges communicate with nodes. And all that this does, again, is update these feature embeddings. So now my feature embedding is not going to be just a CNN that is looking at one image, but it's going to be a CNN that is looking at one image and that has communicated with all the other feature embeddings from all the other images. See who is similar, see who is dissimilar. So what I end up in the output is with a graph which has updated context-aware nodes and also edge feature vectors if you actually also want to use the edge feature vectors. So in order to refine the node features, how we do it within the MPN is we take the node embeddings of the neighbors, we multiply them by a weight, which is of course learned, and then we update the node embedding of that particular sample. So that particular sample contains no longer only its own information, but actually also information about the neighbors. And of course, they are weighted by a weight which is learned during backpropagation. We also have attention scores to actually give different importance to neighbors. So this learned weight depends on the layer and is the same for all nodes, while the attention score depends on the pair of nodes, depends on this relationship between the pair of nodes. Are they similar or are they dissimilar? Okay, let's look a bit more in detail. What is the effect of this MPN for deep metric learning? So if we look at the first step, we have these 4 images, A, B, C, D, which depict these 4 different birds. It turns out that in images A and B, we're depicting the same type of bird, and in image C and D, we're depicting the same type of bird. But the attention scores at the beginning are quite distributed. So between A and B, we have quite a high attention score, less so between B and C, for example, but we want to further refine, we want to further pinpoint these similarities and the dissimilarities. So we're going to do this in a second step, this message passing step and aggregation of information. So again, in this message passing step, we do this for each image. So for example, for image A, I'm going to look at the features of image C, image D, and image B, and I'm going to update my representation by looking at these neighbors. And I'm going to do it in the following way. So you see here that I have my attention scores. These attention scores are going to be multiplied by the feature embeddings. And this is what's going to give me the final updated feature embedding for image A. And so what we will see in the output, essentially what happens after several message passing steps, is that the feature vectors of samples of the same class get more and more similar, and the ones of dissimilar classes get more and more further apart. So you can see here that before the message passing steps, the features of image A and B were similar, but there were some differences. For example, the feature here, while as we do more and more message passing steps, the features of A and B become closer, and the feature of C and D become closer, because these are depicting the same type of bird. We can also see the same in the attention scores. So we see how in the first message passing step, the attention scores were high, but not too high, and they keep incrementing as we do more and more message passing steps. And the network realizes these are actually the same image, so they should have higher attention scores between them. And we see, of course, the same trend between image C and B, which also depict actually the same bird. Okay, so just to recap a little bit, what happens during optimization is that we optimize the backbone CNN and the message passing network in an end-to-end fashion. So there is backpropagation from the cross entropy loss all the way to a CNN. And the nice thing is that now we don't have to select pairs. We just have a cross entropy loss that classifies all the classes that we want. And with this MPN, we're going to be able to refine the CNN features. So one cool thing, though, is that we don't actually need to optimize the MPN, to use the MPN, sorry, during inference. So we do optimize CNN and MPN together, but then we can actually use the CNN backbone during inference. So we don't need to do all the message passing steps during inference, which would of course cost time. What we actually want to do is we do not want to add any complexity at test time. So the nice thing about this end-to-end optimization is that the MPN is going to help us refine the CNN features. Then at test time, we take the MPN, we throw it away, and we just use the feature extractor, the CNN, and perform nearest neighbor lookup like we did for any, for example, for triplet loss or for contrastive loss. So I don't want to talk too much about results. We have state-of-the-art results on 4 public data sets. These are quite varied data sets. We have CARS and CAP, which are like the second one is about the birds that I was talking about. But we also have larger data sets, like, for example, InShop for fashion items or Stanford online products. And even for these really large scale data sets, we are able to obtain state-of-the-art results with the MPN. Now, the nice thing would be to actually understand what the MPN is doing here. So, for example, in order to make a prediction, from which neighbors does a sample rely on? Is this different if we use the MPN or if we don't use the MPN? So what we depict here is the attention scores that we have without the MPN. And we depict it for a particular image and a couple of images of the same class. So we can see here in green, blue, and beige, the different classes. So we have 3 samples for each class. And we can see that without the MPN, the sample in particular has similar relation to all neighbors. So I'm looking at the head of the bird, I'm looking at the tail of the bird, I'm looking at all different images. They all have the same relation to my sample image. So it's trying to look for similarities here and there. With the MPN, on the other hand, the sample actually pays much more attention to samples which are of the same class. So it's not even looking too much at the samples of the different classes. So it doesn't really rely on those samples to actually make a decision. If we visualize the CNN features, so as I've said, these are the features that we want to use at test time, right? We want to completely throw away the MPN at test time, and we want to use the CNN features to actually perform D-metric learning and to check for those distances. So it is important that CNN features are nicely clustered after training with the MPN loss. So here we see our initial features, and the colors correspond to the different classes that we have here. And we see that after one epoch with the cross entropy loss, we have quite nice clusters. So the colors are quite uniform within these clusters. But after one epoch with the MPN loss, the clusters are much more defined. And again, the important thing here to note is that we're not using the MPN to compute these features. So these are the features that come directly from the CNN. And the NPN is just like an auxiliary loss to help train the CNN features. And we see how the CNN features are much better clustered once we use the MPN loss. Okay, so to conclude, I've just presented a method to train neural networks for deep metric learning, but without the need for this careful triplet selection, which usually happens when you use the triplet loss, without the need for complex sampling schemes. The main idea is that we use a message passing network or a graph neural network, which allows us to capture these intra-batch relations, and it allows us to actually obtain stronger embeddings for deep metric learning. And the coolest thing, in my opinion, is that we can get state-of-the-art results without actually using the message passing network at test time. So we're not really increasing the complexity during inference. So with this, I would like to thank you for your attention and also thank my collaborators. And if you have any questions, I will be happy to answer them.
Thank you very much for the great talk, Laura. There's actually a couple of questions in the chat. The first one is from Boyoung, and he asks, can you explain the loss function detail? Is the loss derived from the individual samples or the whole batch?
So the loss is computed per sample, right? So you have a simple cross entropy loss. If you wouldn't have the MPN, what you would do is directly from the CNN embedding, you would compute a cross entropy loss. Is this bird 1, bird 2, bird 3, right? So you have 1,000 classes, simple cross entropy loss. The only thing that changes now is that the MPN changes your feature embedding, right? It looks at the other feature embeddings, updates the feature embedding based on the information on the neighbors, but the cross entropy loss still stays the same. So there's not really much change in the cross entropy loss.
Thanks. Another question is actually two questions in one. The first one is, how is the CNN initialized? And what's the limit on the number of classes for the cross entropy loss?
That's a good question. So actually in data sets like InShop and Stanford Online Products, we have actually a lot of classes. So there doesn't seem to be a problem for thousands of classes in this case. And the CNN is initialized using ImageNet and trained together with the MPN. So the training scheme is actually similar to any deep metric learning paper.
Okay, thanks. Then Andre had a question. If the MPN is not used at inference time, does that mean that the feature obtained after CNN and MPN at training time will be different from the CNN only feature at test time? He's trying to understand how the MPN is helping, since if it's not used at inference time.
So the thing is, so one thing I haven't said is that we do have an auxiliary loss on the CNN feature embedding, still a cross entropy loss. So we do want to bring some power with that embedding to that embedding. And also the fact that we do not use MPN at test time doesn't mean that it's not better with MPN, right? So if we do apply MPN at test time, we obtain better results. But the thing is that what the MPN does is it does this refinement of the features, right? And what we really believe is that this refinement is then back propagated all the way to the CNN, right? So this idea of comparing samples with each other, which is what the triplet loss did, is something that also the MPN is doing. And then when you're back propagating the result and you have an auxiliary loss also on the CNN, you can enforce that the CNN features take as much of that information as possible. This is a bit the intuition that we have for these results. But of course, if you take the MPN at test time, you will get better results, slightly better results. It's not really by a large margin.
Thanks. Then another question is whether you have any experiments using a transformer as a backbone. With the direction of the question is whether a transformer backbone would do the job of the message passing network inherently by itself.
Good question. So actually, transformer and graph neural networks are very, very similar, right? So transformer is an instance of a graph neural network. So what we have in here is indeed very, very close to a transformer, right? So if I go back to, yes, if I go back to the equations, here what I'm basically doing is I'm comparing my neighbors in order to update my own feature embedding, right? So I'm looking at my neighbors and then I am updating myself, my feature embedding with this learned weight, right? So this comparison is also something that happens at transformers. And finally, I also have this attention score, right? So as the attention that we have in transformers. So actually, graph neural networks are sort of the category, the larger category that englobes transformers. And therefore, if you wish, you could view this MPN as a transformer network. Now, this only does the feature refinement, right? It does not do the feature extraction. Another completely different thing would be to replace the CNN backbone with a transformer. Then I believe we could have a very similar effect directly on the feature embeddings.
Thank you. Yorgos had a question. I think he wanted to ask it in person rather than writing here. Yorgos, go ahead.
Hi, thanks. I thought it might be easier. So it was already touched a bit before. So it seems that what is happening is a bit similar to what happens in self-supervised learning in a contrastive manner or not, where you have a backbone and then an MLP and you're optimizing the output, but later on you get rid of the MLP or like there are results that say it's better to get rid of the MLP and do transfer learning with a backbone. So I wonder if something similar is happening here. And actually, if the message parsing network, which is similar to a graph neural network, can be even replaced with an MLP. In this case, what you're keeping is the transformations with the matrices W, which you're learning, and you're not propagating through the neighbors. I wonder if it's something that you tried, you think it could have a similar effect or not.
That's an interesting point. We actually did not try, so I cannot comment too much on that, but it's an interesting thought, especially with respect to semi-supervised learning. So we did also some experiments on using this for semi-supervised learning and doing label transfer and so on. And this also worked quite well. So it might be that with an MLP we get a similar effect. That's actually an interesting experiment that we can do in the future.
Yorgos, does that answer your question?
Thanks. Yeah, thanks a lot. Thanks a lot.
Yeah, sorry, I cannot say more about it, but unfortunately we didn't try yet.
Yeah.
There's another question is whether adding an additional cross-entropy loss to the end of the CNN would help, whether this would make the CNN features like closer to the real problem that you want to solve.
Yes. So we do have that as an auxiliary loss. Let's say I omitted that detail, but we do have that as an auxiliary loss to bring more strength to the CNN feature, especially since we want to use them at test time. So we do have that cross entropy loss there.
A related question is whether, so you see that your approach outperforms the triplet loss. Do you know how it performs compared to like an arc phase loss or other similar losses?
So I can bring up a very boring table here. So we compared actually with really a lot of methods. some of them also try to gather information from the whole batch, especially proxy NCA or proxy anchor, which are actually close to our method. So we did compare to other methods beyond triplet loss for sure.
Another question is whether how the batch size during training affects performance. Is your method like sensitive to this or not?
We do have a bunch of robustness analysis in the paper. Unfortunately, I don't have slides here, but it is pretty stable with respect to attention heads, with respect to batch size. So it doesn't seem to be too affected by these design choices. So that's the really good thing, that it's quite robust. But you can check the paper for the actual numbers, but it doesn't really vary too much. Definitely not below a couple of percentage points, not above a couple of percentage points, sorry.
Another question is that message passing makes the features of all the samples smooth, which might hurt the discriminative performance for some classes, especially with multi-steps. How do you deal with this?
So for the steps that we do, this is not yet visible. So we had done some other works, especially on multi-object tracking, in which we saw this effect, this over-smoothing effect, with which graph neural networks have, that after a few steps, then the features were not discriminative enough. But here we don't do many steps, right? It's 2-3 steps that we're doing here. And these are definitely not enough to over smooth to the point where you could not actually use the CNN features.
Okay. Another question is, does it make sense to try, like it seems that your approach would be compatible with triplet loss. So could you use your approach and then a triplet loss on top of this?
Let me think. So you would instead of the cross-entropy loss, replace it with the triplet loss by selecting some random triplets within the batch. So the thing is that we're not the first works to use cross-entropy loss for deep metric learning. And actually there has been this trend that shows that cross-entropy loss is much stronger for deep metric learning. And in fact, some of these works that we see here, they are using the cross-entropy loss. And the bad thing about going back to the triplet loss is that then you would need to pick again the pairs and the triplets, right? And this is something that we want to avoid here. So we want to just take the batch, perform this computation, and forget about triplet mining. And it would be a bit counterintuitive to go back to the triplet loss. Technically possible, but I'm not really sure it would be stronger, to be honest.
I see. Maybe one final question. Will you have source code available?
Yes, we have all source code available. So you can, I didn't put the link here. I can put it later on in the chat.
Okay. There are a few more questions in the chat if you want to answer them. But thank you very, very much for the great talk. As you've seen, there were a lot of questions.